video for this class, part C.5, examples on Horner's rule. Here I like to give you two examples to explain some interesting things related to Horner's rule. The first example, our example number 3. Given a polynomial with the form, it is a polynomial of degree 4. The highest term, 4th degree. Okay? Yeah. Is it possible that one can find a special case? Special case. Pay attention to this key phrase, such that the number of multiplications to evaluate this polynomial is less than 4. That's the question. Yes or no? Correct or not? Think about it. Special, okay? Yeah. So this form is a general form. And Horner's rule is applied on the general form. Okay? Yeah. So when we learn Horner's rule, it is applied to the general form. Like that. General form, even more general, this 4 is n, right? So, yeah. But the coefficients, no special properties for the coefficients. All right, so now we ask this question just for a special case. That means Horner's rule may not be satisfied, or we can do better than Horner's rule for the special case. That's something behind it. But next thing is, do it. Give a concrete example to show it using a concrete example. Then people will be convinced. You have to show people a concrete example that make it happen, so then people will be convinced. Here, let me show you. Special, I just create a special polynomial. Okay. My special polynomial P of x equals x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. How about that? This is a special degree 4 polynomial, right? Degree polynomial. Now, I ask you this question. What is the minimum number of multiplications do you need to calculate this polynomial? Okay? What is the minimum number of multiplication? Okay, to calculate this polynomial. How about that? Okay, find the minimum number of multiplications to calculate that. Although you can use Horner's rule, if you use Horner's rule, you get 4, right? Yeah, so that's the answer here. But now, because this polynomial has a special structure, it has a special structure, so we can do better than Horner's rule. How about that? Can you discover some special structure for this polynomial? This polynomial is so special. Can you discover it? Do you remember there is a theorem called binomial theorem? Newton's binomial theorem. Yeah, sometimes people also call Newton's formula. Binomial theorem. Okay? Yeah. binomial theorem. All right? Yeah. By binomial theorem, this formula, we can write it as x plus 1 to the 4th power. Binomial, two terms, x plus 1. Then, to any positive integer exponent, that power. Binomial theorem. So you can easily find it somewhere, yeah, on web, okay, yeah. Based on the binomial theorem, you have that. Now I ask you, now you know the structure. The structure is x plus 1 to the 4th power. What is the minimum number of multiplications to evaluate this special polynomial? Can you see that? Can you do that? Okay. X plus 1, that's addition. We do not count it as multiplication. Okay, all right. First multiplication, x plus 1 times x plus 1 equals x plus 1 squared. One multiplication, all right? The first multiplication. Second multiplication, x plus 1 squared, we have that number times same number, x squared number, we get x plus 1 to the 4th. Another multiplication, right? So 1 plus that 1, we have total 2 multiplications. Think about that. So for this polynomial, we only need 2 multiplications. Can you imagine that? 2 multiplications, not 4. Not 4, 2 multiplications. How about that? Okay? So the answer is yes. How about that? Is that smart? Yeah. So for this class, we try to solve computing problems in smart ways. Try to get the point. Smarter ways. Like this. Interesting, right? Yeah. All right. So let's go to the next question. Example number 4. What is the minimum number of multiplications we can get to compute the expression a times x to the 9th power? How many multiplications? Okay, yeah. If you do it directly, one multiplication, x times x, right? Yeah. You need to do 8 times plus 1 here, you get 9. It's not good. 9. It's a not good one. Okay, yeah. Can we use the method we used in the previous example? Previous example, x plus 1 to the 4th. We just used 2 multiplications. Now, x to the 9th. Can we use much fewer number multiplications than 8? Yeah, the previous one here, we use 8. We use 8. Now we want to do as few as possible. Can we use this method here? The method we use here, there is a name for it. So here, let me give the technique that we applied on this example. That's called repeated squaring. Repeated squaring technique. Repeated squaring technique. Here, let us apply the repeated squaring technique another time and see how much better we can do. All right, so x times x, we get x squared. That's one multiplication. Okay, all right. X squared times x squared, repeated squaring. Every time we do squaring, we get x to the 4th. Second multiplication. All right. x to the fourth times x to the fourth, x to the eighth, third multiplication, okay? So then the last one, x to the eighth times x, x to the ninth, fourth, all right? Then a times that, another one. So the total, the answer for this question, 5. Not 9. 4 better than 9, 5. Is that good? 4 better than 9, is that good? Repeated squaring technique. How good it is. How good it is. Okay, repeated squaring. All right. Then, last thing. Okay, last thing. Another interesting property I like to give you here, other than repeated squaring. Can we do a similar technique? So that's called the repeated cubing. Cube, we know cube, 3, you know, x to the third cube, x cubed, right? Can we do the repeated cubing? How about that? Similar to repeated squaring, but we can generalize to repeated cubing. How about that? Although it sounds weird, yeah, but the point is this, okay? All right. X to the ninth equals x third times x to the third times x to the third, right? Cubing, cube, okay? All right. Then x to the third, if we calculate x times x times x, okay? Yeah. So 2 multiplication, 1 here, 1 here. So this one, we need 2 multiplications, all right? When we do here, 1 here, 1 here, so another 2. So the total, 2 plus 2 equals 4. That's the same as we do here 4, right? So for this example, repeated cubing and repeated squaring, same number. But when you go higher, the number will be different, okay? All right, so here, let me tell you, x to the 27th. When you evaluate this one, x to the 27th, okay? If you use repeated squaring, yeah, let me just use this shorthand notation. Repeated cubing, we do 2 ways. Repeated squaring, you can try, you need 7 multiplications. Okay, 7 multiplications. When you do repeated cubing, you need 6. So you can see for this example, repeated cubing can do better than repeated squaring. How about that? Is that interesting? Right? Is that interesting? Yep. All right, think about that. So this is a very interesting question. So think about that. Later, when we have chance, so we will dig a little more on this one if we have enough time. Yeah. All right, so let me stop here, our last video for part C right here.